All right, thanks. So my name is Haibin. I'm from ByteCCL. I'm a research scientist working on machine learning systems. So in today's talk, actually, Mikhail is also joining me. It's a collaboration between ByteCCL and Media on the ByteCCL project. And Mikhail will also cover part of the talk regarding how UCX and some components in ByteCCL are integrated together. So, Mikhail, do you want to briefly introduce yourself?
Yes, I'm a software engineer from NVIDIA, and I was helping Haibin to introduce UCX transport in BytePS. And we achieved some quite good results, and Haibin will talk about that right now.
Okay.
So guys, sorry for interrupting, but at least for me, Haibin, you a bit breaking up. So there might be a connection issue. You may try to disable video and see if it, fix the sound.
Okay.
Pasha, I can hear Haibin quite well, but I hear you interrupting.
Really? Okay. So
Yes.
then it's maybe me. Okay, then you're fine. Then sorry.
Okay. So I guess I'll continue. Yeah. So in today's talk, I will briefly talk about the recommendation model training workload and give some overview of what ByteCCL offers and its architecture, and then Mikhail will talk about the integration part with UCX, and finally I'll talk about some optimizations we did in ByteCCL, and as well as some of the performance result we have, some preliminary performance result we have. Okay, so let's start with the recommendation model training. So for recommendation models, it's actually quite important in the industry. So for many important or successful search engine or social media applications, it plays a very important role. For instance, if you visit Amazon.com and you type some items you want to buy in the search bar, it actually goes through the recommendation system backend, and it promotes some of the top ranked items to you in a very short page, right? So it retrieves from a very large number of items and present only a few numbers of them to you. So it selects very high ranked items. Let me see if I can turn on the laser point. Okay, so in general, the system will collect the all the logs regarding user actions in the backend, and so it knows, for each query which items the user clicked in the history, so that it knows the relevance of the items in the query. So this kind of data is stored in the backend, so that some of the machine learning models can use this data to learn some models. And at serving time, whenever it comes a query, it goes through two stages. So the first stage is the retrieval stage, where we select only a few hundred or 1,000 items from a large pool of, maybe a billion or a million items. So usually the retrieval phase is kind of light, and it does not involve a lot of computation because it deals with a very large number of items. And then with a small number of candidates, for instance, a few hundred, it goes through the ranking phase, where in this phase the model can be more complicated. It can involve more compute with some kind of neural network, and the output of this phase would be a few dozen of items that will actually show up in the page that users see. So in today's talk, I'm actually referring to most models in the ranking phase, where the model is slightly more complicated. It can involve some of the neural networks that people train, and involves large models that can be terabytes of memory involved, and also it's communication heavy. So that's kind of the context I want to provide. And so this is one page that talks about what the model is like, so that you can have some context on what the model actually do. So the model will have two types of inputs. So first of all, some dense features, including some age information or number of views if you're watching a movie. So most of these values are continuous, some floating point numbers. And the other important part is the sparse features. So usually, for instance, if you're watching movies or reading books, there are many different books you can read. So it involves a class of maybe 1,000 or 1,000,000 books, and we cannot really represent them with floating point numbers. Usually we assign some class index to different types of books from 0 to maybe a 1. But we cannot really represent the difference between different books using this number, but rather we would have to have some kind of representation using a vector to represent them in the high dimensional space. So this is what we call the embedding table lookup. So for each book, we have an index representing its index, and we have a vector that represents this book in high dimensional space. And this is what we call embedding, and this is used as the input to some neural network layers that we map this input to some nonlinear functions, and later we can learn some loss function based on it. So this is roughly what the model is like. So in terms of the workload characteristic, very important part is that this sparse feature is related to the very large embedding lookup table, where we have several million items, and for each item there's a vector representing that. So if we have 1 billion items, then the embedding table would be really huge. And if each item has 1,000 floating points represented, then the number of parameters in this lookup table would be 1 billion. So that corresponds to several gigabytes of memory. So this basically brings some challenge in training this model, because this embedding table is huge. And in comparison, the neural network layers are relatively small. It usually only consumes about less than 100 megabytes of memory. So this part is kind of small. And most of the communication happens related to the embedding layer. That's the kind of the characteristics of this workload. Okay, so so how do we actually train this model? So this is one diagram that shows an example of how we train this model. So in this figure, I'm giving an synchronous training as an example, but in practice, there are many ways to do it. And this is one figure I took from Huge CTR, which is a recommendation model training system from NVIDIA. And in this figure, we can see that, so in terms of the parameters, there are two types, the neural network, which is usually very small, and the embedding part, which is huge. So the neural network is replicated across different workers, and the embedding is so huge so that it has to be sharded across the workers. And so this is about the replacement. For the communication part is usually the all-to-all communication primitive, which is used to exchange the sharded embedding lookup result from different devices, so that for each data batch, it contains the sparse feature that is related to different shards in the embedding layer, and the result can be then gathered, used all-to-all, so that it can reform the embedding for this data batch completely, and then feed into the neural network. Okay. So this is like one example of how the recommendation model can be trained, and the primitives involved here is the all-to-all primitive, as well as the all-reduce primitive for the neural network layer. But the neural network layer is kind of small, and the all-reduce usually does not take too much time. But in practice, people have found many other ways to design the system. For instance, here are some design choices of how the system can be trained. For instance, there are some choices of, choosing whether we do synchronous training or asynchronous training. Where in synchronous training, for each training step, there's synchronization involved to sync the states of different workers. So this is usually better for model convergence, but in terms of system performance, it's usually lower because there's some synchronization involved in each step. So that's one difference. And in terms of the communication primitives, it's very different, because for asynchronous training, each worker proceeds at its own pace. So the primitives involved would be some point-to-point operations such as push-pull, similar to send-receive, or gather and scatter. For instance, you can use the gather to gather all the embedding for one data batch, where the embedding are lives in different workers, different worker shards. In comparison, the synchronous training would only use all-to-all because everyone proceed at the same pace. So that's one difference. The other is the embedding placement and the choice of devices. For instance, the huge CTR system is designed around GPUs, and it has very high memory bandwidth and also compute capability, but it also has a very low memory capacity if you compare it to a CPU or SSD. So there are different choices on how we place the embedding on these different devices. And for instance, if we design a system where the embedding is placed on the CPU and the neural network is on the GPU, that means that for the all-to-all or gather scatter operation, the source and destination devices may not be on the same type, right? So there are some optimizations we need to do if they are on different types, depending on the topology. So that's another consideration. Okay. So that's so previously these are about the workload we care about, and ByteCCL is one communication library we designed for this workload, and it's built on top of BytePS, which is already open source. And BytePS is mostly designed around the all-reduce operation to support computer vision and natural language processing applications. And ByteCCL is kind of an extension to it with more communication primitives like gather, scatter, and all-to-all, so that it can be extended to support more use cases. One of the important ones we're working on right now is for the recommendation models. So apart from these 2 points, it also supports both synchronous training and asynchronous training. It's integrated with the multiple machine learning frameworks, similar to Horobot. or the popular ones such as TensorFlow and PyTorch. It also is supporting different hardwares. It supports both CPU and GPU for now. For instance, for the auto variants, we have auto inputs from the CPU device directly to the remote CPU device, or from CPU to GPU and GPU to GPU and vice versa. So there are different combinations that we support and optimize based on the hardware instance types we have. Okay, and so here's the slides about the architecture. So ByteCCL is the communication layer between the machine learning application as well as the hardware. So under the hood, there's another library called ps-lite, which ByteCCL relies on to do the actual communication. So if we look at the ByteCCL layer, it has the framework integration code, for instance, using the TensorFlow API to do some memory allocation and so on. It has some logics about different collective algorithms, such as auto and all reduce, and also some scheduling part related to how we optimize the communication if there are multiple tensors to do all reduce by combining the information from the computation graph from TensorFlow. So it also provides Python APIs for these communication primitives, similar to Hardbot. Under the hood, there's the ps-lite layer, where it provides the C++ interface for control plane and data plane. For the data plane, it's mostly the push-pull API, which is kind of similar to send and receive, but not entirely the same. And then for the transport layers, we have different backends. It has, for instance, 0 and Q to support TCP. We have also the RDMA band to support CPU RDMA memory, and as well as IPC, as well as Fabric band, which runs on AWS EFA, and the new band is called UCX band, which Mikhail works on, help contributed a lot to enable ps-lite to support GPU memory, as well as these different transports. Okay, I guess Mikhail, you can take over and talk about the UCX part.
Okay. So initially we were thinking that UCX would be a good fit for ps-lite, because ps-lite has quite good abstraction for transport layer, and it is enough to implement a certain abstract class to enable new transport in it. And the main motivation for using UCX in ps-lite for us was to enable GPU memory support, multi-rail support, and I think DC is also important. DC is a dynamically connected transport, which is highly scalable, RDMA capable transport, unlike RC, which has certain limits on scale. And with multi-rail, I mean that with UCX, it's possible to use all the network devices which exist on the system for message transferring. And by enabling UCX in ps-lite, we would enable all these features. So that's why we tried to do that. And besides that, UCX exposes many more features, but those are the most important ones needed for this use case. Haibin, can you please move to the next slide? Okay, this is a diagram of UCX layers, which shows what we have here. We have support for various networks. We have support for host memory, for GPU memory, and we have different high-level protocols for different intended for different use cases. And with ps-lite, we used Tech API, which is available as a part of UCP. And we can move to the next slide, please.
Oh, it's stuck. Okay.
Yes. So we used Tech API because at that time it was the most mature API which supported all the mentioned features. And we have a bit more details on the next slide, but in a nutshell, we were using sending function for send messages, and the network polling was implemented based on probing messages sent on the receive. And we had to do some optimizations, and we have some schemes on the next slide. So also worth to mention that it's multi-threaded framework, so we had to use multi-thread support in UCX. And initially we used a model where we used common UCP worker for all the threads, but then we noticed that this is a source of some performance overhead, and we had to do some optimizations. I will talk about it a bit later, but now the common scheme is that for implementing transport layer in ps-lite, it is enough to implement just a few communication methods in the abstract class. And for sending message, it is required to send two messages actually. One is metadata describing the payload which comes right after it. And so it's on the sender side, it's just implemented by using two text sends. And on the receiver side, we have a polling thread which is constantly probing the network for specific tag, waiting for the meta message describing the payload. And once we notice that we receive some meta message, we take all the details from it, like length of this message, its ID, etc. These details are needed to allocate a proper receive memory buffer to get the message into. It's not really a real memory allocation because we have a specific memory pool on the receiver side, but we have to know certain details to get the proper buffer from this memory pool. And then we call take receive function, which gets the payload itself. And once we get the message, everything is done in this polling thread. Well, once we get the message, we push this data to the receive thread using thread safe queue. And then the message comes to the upper layer, to the application. And that's the scheme. And that was initial implementation, and we had to do some performance optimizations afterwards. At first, we tried to optimize performance for relatively small messages, and we implemented so-called short protocol where we bundled metadata together with payload. We just used UCP IOV type, and we started sending just one message instead of two. The drawback of this protocol is that it doesn't support GPU memory yet because it uses IOV data type, but it noticeably improved performance for small message sizes like 100 of bytes. When I say small message sizes, I mean 100 of bytes or maybe up to kilobyte. Also, as I mentioned before, we noticed that using a common worker for all the threads introduced quite notable performance overheads. So we divided. We started using different workers for sending and receiving threads. that helped us to avoid logs, many logs on the data path, and also have been added lockless thread safe queue to the BytePS, and that also helped to remove some logs and improve overall performance. And another important optimization was to implement separate UCX context per GPU device on the system. And the motivation for this optimization is that currently UCX during startup selects the most optimal devices and protocols based on internal analytics, which UCX will use for communication, but it doesn't take into account memory type of the data which is being transferred. Currently, it's not taken into account by UCX, and due to this fact, UCX, when during initialization, selects a certain HCA or network adapter for communication, and if we have a bunch of them, as well as a bunch of different GPUs, like for instance we have on DJX systems, it may be quite inefficient if we trying to send some memory, some buffer residing on the GPU memory, which is located quite far from the network device which was selected by UCX. So we did it this way, that we created different UCX context per each GPU device, telling UCX which GPU is currently enabled before creating every context, so that UCX would select the proper HCA or NIC for that. And then in BytePS, then we made a mapping in BytePS and in UCX transport, that once we get some GPU memory to transfer, we also get a device number which this memory belongs to, and based on this information we select a proper UCX context to use for the transfer. And this really helped to improve the performance, and it may sound like quite a complicated scheme, but currently we have a new version of protocols under development in UCX, which would account this, which would take into account memory type, and once it is implemented, we will not need such a complicated scheme anymore. And actually, I think this is most important optimizations we did. So I think I'm done.
Okay, I'll continue with the rest part. So there are some optimizations we did in the upper layer as well. So for the first one, it's similar to what Mikhail said previously regarding, the topology and the NIC affinity. So we have machines that in practice do not have very balanced NIC affinity. For instance, we have instance with 8 V100 GPUs, but only with one NIC with 100 gigabits per second bandwidth, and this is close to one of the PCIe switch, which is shared with some of the GPUs. So for this case, we would turn on send GPU memory directly if the GPU is close to the NIC, and for the rest of the GPUs, they would have a CPU staging buffer to send it out. Apart from this, we also have some logics to in BytePS in general, just to use the shared memory if the sender and receiver are on the same node. We initially tried UCX shared memory transport, but we didn't find it as fast as we expected, so we had some workaround. Apart from that, there are two other points regarding concurrent primitives and also asynchronous support. So we looked at some existing options, for instance, Nickel, but we found that Nickel does not support concurrent calls. For instance, if we have an all reduce on one stream and auto on another stream, it may block itself in-house. But for ByteCCL, it's not an issue, so it can have multiple operations happening concurrently because underlying ps-lite and UCX layer is thread safe, and it can process all these communication calls concurrently. The other point is it's more asynchronous in the sense that we compared it with Horvath, where in Horvath there's always some negotiation before any MPI calls can be invoked. So it requires some coordination between all the workers so that if one of the workers is not ready for all-to-all, it will not really start the MPI call. But in ByteCCL, it's not. There's no explicit synchronization needed when we do an auto-all, and we track all these asynchronous requests and callbacks by the UCX callbacks. So if one worker started early, it's faster than other workers, it can start the auto call earlier by sending it to its peers if the peer has already allocated the memory. Okay. So next slide has some performance results. Okay. We have some preliminary numbers for two models we train on. Either one of them is on CPU, the other is on GPU. For the CPU model, it's around 1 TB of memory, and we train it on a CPU cluster with 4 nodes, and each one is equipped with 200 bps NIC. And we compare with the Horvath plus HPCX, and we saw around 12% end-to-end speed up of training this model. We didn't do very detailed micro benchmark on the auto and all reduce primitives. We only benchmarked it with the message size we care about. But with the micro benchmark, it's kind of slightly faster or similar to what Horvath offers. On the GPU side, we also tested with a 16-node GPU cluster, each with overall 800 Gbps networking bandwidth, and each one has 8 A100 GPUs. The model size is slightly larger, and we compared with a Nickel op in TensorFlow, and we saw around 8.6% throughput increase. And on this model, we also did some micro benchmark on the auto throughput, and it is on par with Nickel. And I think Nickel is very strong baseline, and we're actually very. I think the 8.6 speed up is already pretty good. This is the final part. So there's some pain points around UCX when we tried it and benchmarked it. For instance, some problems arise when we benchmark the internal performance. Some of the CPU to CPU transfer is not as fast as we expected, and the CPU to GPU transfer is actually very slow. There are some other pain points, such as some confusion on the prefix support on the configuration. For instance, some of the UCX environment variable does not support prefix, and it's not very clear to the user which ones are supported. And finally, there's some future work we're thinking about. For instance, for some of the systems we have internally and also in the community, the machine runs more than one microservice, and there's some non-UCX traffic that's occupying some of the NIC bandwidth. So with UCX multi-rail, it's always split evenly if it has multiple rails, if the NIC are of the same bandwidth, but it doesn't know, some of the NIC are already busy with some of the some other workload. So there's some space for workload balancing for this scenario. And also, of course, ByteCCL is not fully open source yet. It's built on top of BytePS, and we're looking at cleaning up the code and making it fully open source. And yeah, this is the final slide. Many thanks for many supporters from NVIDIA and Manlogs, and big thanks for them. And we can take questions now.
Hi, Ben. Thank you very much for presenting this. Any questions from people online? If not,
I just have a quick question about handling multiple UCP contexts for multiple GPUs.
Yep.
Yeah, I was just wondering how then this affects the number of endpoints that you create, and how the endpoints are created when you have multiple UCP contexts. Like, do you create one endpoint from every worker of every context to every worker of every other context?
Yes.
On every other node?
Yes, currently it works like this. We establish connections in auto fashion.
Okay, and how's the scalability of that? Does it really have any significant impact on resource usage?
The priority was the performance here, because scalability was not really pain point. And yes, it's not really efficient in terms of resources consumption. And as I mentioned, this is an intermediate step going to protocols version 2 in UCX, which is not ready yet. But yes, it's quite resource consuming solution.
Well, I'm actually asking more because I'm actually implementing something similar. So I was wondering if that's how you do it. And do you establish the endpoints eagerly at initialization time and connect all the contexts together, or is it like established on demand using client server?
We establish it in the very beginning, but that's how ps-lite works. Because Haibin, please correct me if I'm wrong somewhere, but the ps-lite has 3 communication entities like scheduler, worker, and server. And in the very beginning of the program, all these processes are starting up, and scheduler establishes connections with all servers and workers, and servers and workers establish connections between each other. And it's done on the initialization phase. So it's not dynamically connected. It's connected statically at startup.
All right, so you already have all the connections.
Yes.
Great.
But it would not be difficult. I mean, it's not really a problem to implement dynamic connection in such a scheme. It just doesn't fit the API of ps-lite, of the way it's being used by the applications.
I see. Right. All right. Thank you.
Any more questions online? If not, I have one question. Is Michael, probably for you? Did you figure out why shared memory doesn't perform well? Because we kind of have been optimizing shared memory CPU to CPU specifically for a while now.
Yes, we're analyzing that together with other team members, with Marina and Dmitry from our team. And actually, I think the main issue we're talking about is that UCX comparing to RDMA WAN doesn't perform well on shared memory, because RDMA WAN, it's called RDMA, but actually it has IPC capabilities inside as well. So it utilizes IPC shared memory, but it starts four threads for shared memory transfers. And that makes, and in UCX, the best performance we get is we can achieve is using XPMEM, but we have to do some additional changes to enable it. There are some complications related to client-server communication model, etc. But that's not the biggest effort. The much bigger effort would be required to implement several threads for copying the data.
So they have multiple cores essentially pushing the data. Do you know if it's copy in, copy out in their implementation, or is also some sort of zero copy?
If I'm not mistaken, it should be copy in, copy out. Habin, do you remember?
It's not zero copy. It's not. Yeah, it's copying in and out.
I see. So it's just multi-threading.
Yes.
Okay.
And also, we had some different issues with GPU to CPU memory inside the host, but there are a lot of topological things to discuss here. So it's hard to answer because we had a bunch of issues with different root causes.